Good evening. It's a pleasure to be here, and I'm quite pleased at the turnout and the crowd that we've got tonight. As all of you know, we're here in large part to mark the 15th anniversary of the launch of the Chandra X-ray Observatory. Joseph gave a background on me. Let me tell you briefly about my association with Chandra. I came to work at NASA in 1985 out of college and went to work on the Hubble Space Telescope program. As we were nearing the completion of it, we started working on a program called AXAF, as many of us fondly remember it being called, the Advanced X-ray Astrophysics Facility. In 1988-89 timeframe, I was asked to go down as we were preparing Hubble for launch to start working on the Source Evaluation Board to select the prime contractor that would build AXAF or Chandra. In 1992, we went through a major restructure of the program. You'll probably hear more about that from our panelists in a few minutes. But following that, I worked throughout the development phase on Chandra, leading up to the launch in 1999, and as Joseph mentioned, continued in the operations and science phase, and in 2003, succeeding Tony Lavoie, who was the program manager following launch, I became the manager and stayed with Chandra up until a couple of years ago when I came to work on the Space Launch System program as the program planning and control manager. And now, most recently in the last few months, I've been named to the SLS associate manager, program manager position. But enough about me. Really what we're here to talk about tonight is Chandra and the wonderful science that has returned, as well as the fine operations that the spacecraft has seen over these past 15 years. As we all know, July 23rd, 1999, marked the launch of one of NASA's 4 great observatories. 15 years later, in fact 15 years ago yesterday, Chandra continues to operate near perfection and produce world-class science that's unrivaled by any currently operating telescope and any presently conceived X-ray telescope. So what many of you in this room helped put together 20, 25 years ago, you're now seeing the results and the fruits of all the work that you put into this through the science that's being returned today. It's a lot to be proud of. Marshall Space Flight Center has the proud distinction of being involved with the program really from its initial phase. From the conception and the proposal made to NASA by SAO's Harvey Tannenbaum and Nobel Prize winner Riccardo Giacconi in the late 1970s, to the design and development phase of the 1990s, leading to its launch in 1999, and throughout the 15 years that we've seen the outstanding operations. It's been with much pride that the Marshall Space Flight Center has been NASA's lead center for management and science operations of the telescope. With outstanding partners like the Smithsonian Astrophysical Observatory, TRW, now Northrop Grumman, MIT, Penn State, Eastman Kodak, and many others, Chandra has proven to be one of the most successful missions that NASA has ever undertaken. What you will see and hear tonight are some of the challenges that the program and the team went through in getting Chandra ready for launch, and some of the highlights of the outstanding science results that we've seen. So with that, before I introduce the panelists, we've got a short video. It's about a 5-minute video that was actually done as a companion to a paper that Dr. Martin Weisskopf, our Chandra project scientist, recently authored. The film in the paper is entitled Highlights and Discoveries from the Chandra X-ray Observatory. So with that, we'll take a view of the video.
Hi, I'm Martin Weisskopf. I'm one of the co-authors of this wonderful review paper about 15 years of the great science that has been done with the Chandra X-ray Observatory. My co-authors are Harvey Tannenbaum, Wallace Tucker, Belinda Wilkes, and Peter Edmonds. The observatory was designed for 3 years operation with a goal of 5, and we are now entering our 15th year. The heart of Chandra is its beautiful X-ray telescope, but in point of fact, Chandra is extremely necessary because its angular resolution is so well matched, because you'd like to take a Chandra image of a region of space, for example, a star-forming region, and a Hubble image of the same system, and then overlay them. And if the angular resolutions don't more or less match, you're just going to see blurring from one or the other. And the paper just shows the broad depth of scientific capability of Chandra. When you read the article and go through the various sections from normal stars to dark energy, you will see a large number of topics that are covered. So it may surprise one to know that Chandra has made a contribution to the understanding of exoplanets. We found cases where a Jupiter type sized planet is actually interacting with and affecting the X-ray emission output from its companion star. From the beginning of Chandra, its first official first light image of Cassiopeia A that discovered, lo and behold, the compact object, to more detailed spectroscopic studies that have shown that the explosions are not symmetric, that you don't just find this hierarchy of hydrogen, helium, etc., down to iron. Chandra has constantly made interesting new discoveries, and this continues today on supernova remnants, where we're learning and looking for the sources of gamma ray flares in studying the crab, both with Chandra and also with Hubble. The phenomena of cosmic feedback involves the question of what happens when a supermassive black hole, which form at the center of galaxies, forms a relativistic jet of particles, and these particles roar out into the galaxy and even into the intergalaxy medium in clusters of galaxies. When they do so, they remove material because of the energy, and this then starves the supermassive black hole, so the jet doesn't have as much energy. Then after a while, everything cools off and more material can be accreted. This is a way of continuing the process of galaxy formation and influencing galaxy and star formation, and something that Chandra can contribute to in a major way. Probably two of the most exciting and interesting topics in astronomy and astrophysics today are called dark matter and dark energy. The example is what we call the study of the bullet cluster of galaxies. And this is a train wreck of clusters of galaxies. In fact, two clusters have collided. And what you see is that when these two clusters collided, the normal matter interacted and sloshed around. The dark matter just stayed where it was. And then another area that we didn't know that Chandra could contribute to was the study of dark energy. How do the great clusters grow with time? And if there is dark energy that's accelerating the universe apart now, they will grow in a different way than they would if there wasn't. And then, of course, a fascinating thing, both from a scientific point of view and for the layperson, too, is that the equation of state, the number comes out -1, which is precisely the cosmological constant in Einstein's general theory of relativity. There are many experiments that we can point to right now that need to be done, and they're discussed in our paper. And as the past 15 years have shown, there are plenty of surprises out there still yet to come.
Very nice. With that, what I'd like to do now is introduce our panelists for tonight. These three gentlemen here I'm proud to say, are very good friends of mine and mentors of mine over the many years that I was associated with them and continue to be associated with them. So with that, first I'd like to introduce to your left, nearest to me, Dr. Martin Weisskopf. Martin is project scientist for NASA's Chandra X-ray Observatory and chief scientist for X-ray astronomy in the Space Sciences Department at Marshall. Martin received his doctorate in physics from Brandeis University in 1969 and began his postgraduate career at Columbia University in 1969, where he became an assistant professor and performed many pioneering experiments in X-ray astronomy. In 1977, Weisskopf left Columbia to become senior X-ray astronomer at Marshall Center and Chandra X-ray Observatory project scientist. Martin has served on numerous committees, including the National Academy of Sciences Panel on High Energy Astrophysics, Astronomy and Astrophysics Survey Committee. He is a member of the American Astronomical Society and its High Energy Astrophysics Division, the American Association for the Advancement of Science, the International Astronomical Union, Sigma Chi, a scientific research society, Phi Beta Kappa, the National Honor Society, and a fellow of the American Physical Society Astrophysics Division. Martin has held numerous special appointments during his career. He is a senior co-investigator of the European Space Agency's International X-ray Imaging Experiment and the originator of a major experimental research program that began in 1978 that currently concentrates on the development of X-ray optics. Our next panelist in the center is Mr. Loe Tally. Fred served as manager of the Chandra program, the Observatory Projects Office at Marshall from 1988 to his retirement in 2000. Fred's responsibilities included managing and coordinating project planning, budgeting, scheduling, engineering, design and development, testing and evaluation, and operations planning and development of the Chandra program. Fred came to Marshall in 1960 when he transferred from the U.S. Army Ballistic Missile Agency to the Marshall Center's Guidance and Control Division and the former Aeronautics Laboratory. Fred held a number of positions at Marshall with increasing responsibility, including Chief Systems Division of the former Aeronautics Lab, Manager, Applications Engineering and Use Information Office, and Deputy Director of the Electronics and Control Laboratory. In 1975, he was named Chief Engineer for the High Energy Astronomy Observatory Program, a series of 3 astrophysics observatories that were launched between 1977 and 1979. Fred was appointed Associate Director for Engineering and the Science and Engineering Director at Marshall in 1980. He was selected as Director of the Information and Electronic Systems Laboratory when it was created in 1982. In 1983, Fred was assigned to the Hubble Space Telescope project as Deputy Manager for Systems Engineering and Integration. In 1986, he became Deputy Manager of the Hubble Space Telescope program and held that position until his selection as Manager of the Observatory programs. From 1988 to 1991, he served as Project Manager for both Hubble and Chandra. And finally, to the right, your right, is Gene Oliver. Gene served as Deputy Manager of NASA's Chandra X-ray Observatory program and Acting Manager of the Chandra Operations Office. He was appointed to this position in 1988 after serving 14 years as Chief Engineer for the Hubble Space Telescope project. Gene's major duties involved managing and coordinating project planning, budgeting, scheduling, engineering, design and development, testing and evaluation of the Chandra program and its systems, including support equipment and facilities. Gene came to NASA in 1964 as a senior project engineer at Kennedy Space Center. He transferred to Marshall's Future Projects Office, Research and Development Operations in 1965. He served in several progressively responsible positions. In 1969, he became Chief of the Astronomy Group in the Mission and Payload Planning Office within the Program Development Directorate. He was named Chief Engineer of the Development Team for the Hubble Space Telescope in 1973. In 1974, Gene became Chief Engineer of the Hubble Space Telescope project until he assumed his duties with the Chandra program as the Deputy Program Manager. So quite an esteemed panel that we have here tonight. Let me kick it off first by asking Martin, if you would, tell us a little bit about the science behind Chandra.
Thank you. That's an extremely interesting question, and the science behind Chandra goes back to 1962 when X-ray astronomy began, other than solar X-ray astronomy, with their sounding rocket experiment that Riccardo Giacconi did. He discovered the first non-solar X-ray source, but he also discovered something else, and that was that there was a glow of X-rays no matter where the sounding rocket looked. And that became known as the diffuse X-ray background. And the big question was it truly diffuse, or was it made up of objects that, because there was no angular resolution in those early experiments, that you just couldn't see? So you couldn't resolve what was happening. And Ricardo in 1963 figured that you needed a 1 meter diameter, 10 meter focal length X-ray telescope to answer this question with about 1,000 square centimeters of area. And lo and behold, he was right. And the background eventually was resolved by Chandra, and it turned out to be discrete objects. So that's really the driving science behind Chandra, although there were many other goals. And since he thought of this after 5 minutes of data in X-ray astronomy, I think you can understand why Ricardo won the Nobel Prize in 2002 or 4, I forget which.
Martin, in the way of a follow-up, Dr. Paul Hertz, who is the head of the astrophysics division at NASA headquarters, in congratulating Chandra on its 15th anniversary, he was quoted as saying, "Chandra has changed the way we do astronomy." Can you elaborate and explain this a little more?
Well, it's an interesting question. I think the basic change has been to convince all astronomers and astrophysicists that you can't understand astronomical objects, anything from planets to comets to stars, normal stars, galaxies, clusters of galaxies, dark energy, dark matter, without also studying the X-ray emission. The old analogy was that you can tell something about a human by studying the foot, but you can't tell all.
Right. For a moment, we'll move away from the science side of the program to the development of the hardware. Fred, let me ask you this. What would you say was the most challenging time for the program?
Well, before I get into that, because I have to think about it a little while, but with all the things you said about me, about my career and so forth, I think the center had a hard time finding where I could do a good job, and they kept putting me in different ones. But I'm glad they ended up making me the program manager for the, at that time, AXAF satellite, and because I ended up with an awful lot of good people and very talented people. Some are here. Definitely, a lot of them were at the Marshall Space Flight Center. At one time or another, I think we had just about every person in some capacity working on a piece of Chandra. And that's the other thing I'm going to do is, instead of saying AXAF and Chandra and so forth, I'll stick with Chandra because that's the final name that ended up on the satellite. Well, to me, there were many places in the program where we had an awful lot of trouble, and they were very taxing and so forth. But at the very beginning, before we had even had a new start, and Chandra was always going to be a new start as long as the Great Observatories program was going to happen. At about, and if I get the dates wrong a little, you have to understand that when you're 84, you don't remember dates very well. It was about 1987, and Martin and his colleagues at the Smithsonian, Harvard Smithsonian, and other places had done a good job of convincing a majority of the science community that the next big new start should be the X-ray Observatory and later on called Chandra. Now that all sounds good, and even the Russians and the Japanese were out there helping us. They were both planning X-ray observatories and planning to beat America to the punch of discovering a lot of X-ray great things. But even with all that, it didn't make it so. Congress, as always, even now, is in a bind for finding money and where it should be put. And so at about 1989 or so, they decided to have a fellow that convinced them approach us with a challenge. The fellow that convinced them was named Richard Mallow. He was the chief staff assistant to, at that time, the chairman of the Appropriations Committee. And I think his name was Boland, but I'm not positive. Anyway, Richard Mello was a very smart person, and he probably had more time in the Appropriations Committee than anybody serving on that committee, because he'd been staff assistant to the chairman's for about 16 years, and a lot of these other fellows, you know, they'd get reelected or not, and new people would come in. So he was very much listened to. And he approached NASA and asked, what is the most difficult thing that you can do at this point in the game to make this telescope a success? And the answer was, because we didn't know it was downstream of what was going to happen, but what had to happen to make it as good as we were promising, we had to build the largest set of mirrors to specifications, and then prove with X-rays that it actually did what we said it could do. And what we said it could do is that it would take the impinging X-rays on these mirrors and funnel them down after the X-rays bounce from one surface to the other, and they would end up at the focusing position no larger than 1/2 of an arc second. Now, as an example anyway, an arc second, if you read the paper and look at the end of a sentence, the period there is roughly an arc second across. Now, we had to have 1/2 of that. And did we have a picture of the X-ray mirrors? Well, they're cylindrical mirrors, and not the type that you always look at yourself when you're shaving or other things. They're cylindrical mirrors, and the way they work is that X-rays that are coming down there, if they saw a flat surface in front of them, they would embed. So you can't do that. You've got to bend them to where you want them to go. So these mirrors are very much, you know, able to do that if they're created in a parabolic fashion, which is a slope in one direction, and a hyperbolic fashion, which is a slope in another direction. When you put these two together end to end, then they can do the job for you. And plus, they have to be very, very smooth, because any object that impinges on that glass surface at a very small angle, if it meets an obstruction, it'll just embed itself. So in any event, that was, you know, the process that we'd have to go through. Now, this is the scary thing. The challenge that we got from Congress was build the largest set of mirrors, do it in a fixed amount of time that it was going to be established, and then test them with actual X-rays and prove that you've met your requirement of a 1/2 arc second. Now, if we didn't do that, there would be no project, or at least no project for a long time. No funding would come across. So we all did what we always do. We worked together at that point, but several things had to be done. First off, the purchase of the mirror in blanks that were not sloped yet or polished. And that was done by contracting with a company in Mainz, Germany. And I think it was Schott Optical Glassworks. They made large billets of this material, which was it wasn't really a glass, it was a ceramic. And another side light of the thing is that material recipe was founded in the United States, and the company that did that sold the rights to manufacture it and sell glass of that material to Schott in Mainz, Germany. All right, so we contracted for that. That was one of the principal things. At the same time, Perkin-Elmer, who was our manufacturer, to actually manufacture the shape of the mirrors on the inside and calibrate them and so forth. they had to do several things that were not easy. We knew we had one step forward. We knew we could do this because we built a set of mirrors that were quite a bit smaller, and they had the specifications that we had on these larger mirrors, and we actually proved with X-rays in the Marshall X-ray calibration facility that they did focus as we needed it. But now you had to scale up all those machines from what they were to something much larger to do the rough grinding and the polishing. And then you had to scale up the metrology stations, which were measuring stations, to be sure you had the right slope and all the smoothness that you needed. So that was a tremendous job that PerkinElmer had to accomplish. In the meantime, at the Marshall Space Flight Center, since we had to do this the testing with actual X-rays, the X-ray cal facility that was used and developed for the Einstein Observatory as part of the HEO project had to be expanded also. That required taking the source generation building and equipment, moving the source generation building, and it's advancing the quality of the generation equipment. In doing that, we also had to extend the vacuum tube that goes between the source generation station and the chamber where we would put the Chandra mirrors to be tested. And we expanded that chamber to handle all of the testing that would have to be done for Chandra. So it had to go from what it was to something like, if I remember correct, 20 feet by 75 feet long. The vacuum capability had to be made better. The thermal capability had to be made better. And the whole system where the equipment would go for testing in the chamber. So the chamber had to be vibration isolated to a maximum so that cars going along the road besides that facility and trucks would not cause the items under test to vibrate. So all that was being done. At the same time, we had the attention of the center directors. He was very much interested in what's happening, so 3 times a week we would meet with him in the morning and tell him all the progress that was being made against the schedule. And where we had problems in funding, he tried to help us there as best he could. And all of that was made and done by the Marshall Space Flight Center, and on the day that the mirrors were finished at PerkinElmer, they were sent to Kodak in Rochester, New York, where they were mounted in a test fixture, and it was then sent to the Marshall Space Flight Center. At Marshall, we had a division of responsibility for doing the tests. We agreed on the engineering side and the project side to do everything that had to be done to the chamber to be sure that it was operating properly and so forth. But all the testing was under the direction of the science people that could do a better job than we could in developing the test program and then evaluating it. This was done, and Len Fisk, who was the administrator for science at NASA headquarters, was there to see the results. Amongst a lot of people at Marshall and the science community, the results were that we bettered the requirement from a half of an arc second, half of an arc second. We came in a little under a quarter of an arc second. Now that is small. This mirror, the largest mirror, the diameter of that was, I believe, 42 inches. And that meant 42 inches of X-ray content was squeezed down to less than a quarter of an arc second. Amazing. All right, so, we were all elated. Fisk went to headquarters and to Congress, and he told them all the nice things that happened. And Mallow, again, representing the Appropriations Committee in Congress, said, "I congratulate all of you. You did great. I have some good news and some bad news for you. The good news is you have a program. The bad news is you're not going to get the funding that you want." So, I see Al Bellingrath smiling. So what happens when you don't get the funding that you want, but the requirements in the program stay the same? You still had a 15-year mission, so you had to have servicing and all the other things. If you can't do the things that you'd planned in 1 year because you don't have the money for that year, but eventually they have to be done, the only way you can do it is you work longer. So that means the launch date that you had planned gets moved out further and further. And secondly, because you have a larger workforce on board when this movement is going on, your final run-out money of what the total project cost is will get larger and larger. And that's what happened for 2 years. And then NASA headquarters again, and they were right, said, if we don't do something about this, they're going to cancel us anyway, because they can't, afford to spend more money than had been allocated. And if we don't launch on time, that's going to happen. So we finally convinced everybody, and probably myself more than anybody else. But anyway, we started to restructure Chandra from being what it was to what it would have to be. And if I can remember some of the things that we had to do, first off, we had to get lighter. And the reason we had to get lighter is that we wanted to go to a very high elliptic orbit, 100,000 miles by 10,000 kilometers, 100,000 kilometers, excuse me, by 10,000 kilometers. Reason for that is, if we were in low Earth orbit like a Hubble, we would only have, very few times that we could actually view the sky. By going to this high elliptical orbit, there was a majority of time that we would be free to look any place we wanted to. And therefore, the high elliptical orbit had an orbit time of approximately 3 days. If you're in a low Earth orbit, you go around the Earth at least 17 times a day. So this was to get more viewing time, because our mission time was cut from 15 years to 5 years. And that needed to be done. And to get to that high Earth orbit, we had to also depend on several propulsion systems. One was the shuttle. Then the shuttle would be take us to a low Earth orbit. Then we had an IUS, which is inertial upper stage, and that took us to an intermediate orbit. And then TRW had to design an internal propulsion system that would take us to the final orbit. So that had to be done as far as building a new propulsion system. We cut down the mirrors from 6 pairs to 4 pairs. There was one experiment that was taken off to be flown at a later time, and that was done. And let's see, what else do we have to do? Yeah, I think that's about sums it up, but those were quite difficult things to have accomplished also. I think that about does it for what I can remember about it.
Thank you, Fred. That was very good. Gene, let me ask you, what would you say were the major lessons learned that you took away from the program?
Well, in the first place, the management team on Chandra, to a large extent, was the same management team we had on Hubble. And we rolled essentially off of Hubble right into Chandra. So from a lessons learned perspective, it's easy to get Chandra and Hubble kind of mixed up, because many of the lessons that we would attribute to learn from Chandra, we had actually learned from Hubble, and we just applied these into Chandra. One of these, for example, is the importance of independent cross-checks on all your formal verification activities that you're doing. We'll learn that in spades on Hubble, particularly on that primary mirror where we didn't have a second way to verify that what the test gave us was accurate. So on Chandra, we really did that in spades by doubling up on all of our testing at the element level on the optics as well as an end-to-end test. So we had many cross-checks on the optical testing. We applied that same strategy to many of the other activities beyond just the optical testing. Anytime you're verifying hardware by analysis, you should always have a backup analysis done by some independent organization with a different model to make sure that the guy that did the first analysis didn't just have a bad day and make a mistake. It's kind of like a single point failure, if you will. So we learned that from Hubble and we moved it over into Chandra. And that's probably one of the biggest lessons we learned here, and we applied it to the Chandra program, was double cross-check everything you're doing, whether it's analysis or test. Another one that comes to mind is the fact that when you're building a database to operate a spacecraft, if you don't plan at the very beginning to just have one operational database, you're going to wind up late in the program with a handful of different databases that you've then got to convert into one to operate it with. That's a lesson we didn't learn in Chandra, but we'll do it better next time. Number of the programs that I've been consulting on since I retired have applied that strategy to the development. The simplicity of having right at the very beginning of the program the development of one database for operations and then directing all other activities in integration and test to use the same formats, so that's one integrated database from the very beginning, makes the life a lot easier. In Chandra, we had a spacecraft developer that had their own independent test database for all of the different commands, telemetry, procedures for operating all the hardware, the storage of their onboard software, and all of that stuff was in a database that the prime contractor had. Well, he had delivered to him a telescope which had been checked out by another contractor with a different database. And the science instruments were developed by multiple contractors with different databases. And it was real fun late in the program for operations to come in and try to figure out how to make one database that would work for ops. That was fun, I'm telling you. So that was a lesson we didn't learn, but we will next time. The other thing that I think is important is that we need to know right up front and to recognize the importance of systems engineering in a program. It takes a lot of manpower to do a good systems engineering job. And when you're right in the very beginning of a program, particularly if you've got major contractors that you're trying to get on board, when they turn in a proposal to do the development that you're asking for, they're operating in a very cost-constrained, competitive environment. And that means they need to turn in a proposal with a low enough cost that they have a good chance of winning it. Now, if you just look at it from a simplistic perspective, if you have a proposal that has a certain amount of dollars, say, required for developing a structure, well, anybody can envision a structure. A bridge has a structure, buildings have structures, and spacecraft have structures. So you can wrap your mind around that, and you can begin to try to figure out how much manpower it takes to make that structure. The same thing for electronics, the same thing for communication, all across the board where there are just subsystems that have to be built that you can think about and envision your mind. You can cost that out and feel pretty confident about it. But systems engineering is a broad thing. It includes trying to develop the requirements and flow them down and make sure that you know what you're trying to develop. It includes doing all kind of systems level analysis that go beyond just basic hardware elements, keeping up with all the interfaces with all the contractors you have on board, and ultimately being involved in concurring in the verification process that all of this stuff has to go through when it comes together. So what we found in Chandra, and also what happened to us to a certain extent at Hubble, was at the beginning of the program, you select contractors, but you realize later in the program that they underbid the systems engineering. And now you've got to start scrambling to get systems engineering back up to a level that can actually do the program. So that's something you have to apply right up front and try to make sure that you cover that in your very initial structure, or you're going to be scrambling late and maybe miss something. There's a number of other lessons that we learned. In fact, that the agency recognizes the importance of lessons learned. They form a management team to manage any spacecraft program that they have. And although NASA gives plenty of specific guidelines on how to design hardware, how to verify hardware, how to control contractor costs, how to measure their performance, there's still a myriad of daily decisions that the management team has to make, that the only way they can make them is on their own experience and their own ingenuity on what needs to be done. And the lessons learned that you can apply from one program into another are very important. And that's why the agency requires that every program at its completion develop a lessons learned document. I think in Chandra we have about 19 of these things. So there's a lot of lessons that we learned and a lot of lessons that we'll apply the next time. And that's about the three that I think would probably most stands out in my mind. Thank you, Keith.
Yeah, thanks, Gene. Martin, Fred alluded in here during his discussion about the X-ray calibration facility here at Marshall. If you could maybe talk a little bit about the work that was done there and what its ultimate importance was to the success of the mission.
Yeah, the existence and the use of the calibration facility served a number of purposes, all positive. First of all, we were building an observatory that was much better than anything that had been flown before. So we had no standards to calibrate against on orbit. We really had to calibrate the X-ray performance on the ground before we launched it. No question about it. But there were other benefits, and I think just briefly, one of the most important was it gave our Science Center an opportunity to have to deal with flight light data from X3, from the observatory, in a situation where they were under no pressure to deliver. Because those of us involved from the science instruments, from Marshall, from the contractors, we were, of course, taking the data through our GSE, ground support equipment, and had to be able to analyze it in real time. So this was a great practice session for the ground system to be able to deal with. And I think the final thing was a very, very important intangible. The calibration took 6 months or so. It was 24 hours a day, 7 days a week, except for having to leave the building occasionally for a tornado warning. But it brought elements of all of the systems together under very close circumstances. Contractors from the spacecraft side, contractors from the telescope side, Marshall Space Flight Center, engineers, scientists, and managers. And we became we rather than us and them. And I think that was extremely important from the period from 96, end of 96 onwards until launch to make Chandra the success that it was and is.
Okay, thank you. Turning more to the personal side of it, for all three of you, do you have a favorite story about launch that you'd like to share with us?
I always have a story. Chandra was the first shuttle mission that was commanded by a woman. Eileen Collins. Mission specialist Katie Coleman was also on board. She took a lot of nice pictures of when they released us from the shuttle. And Jeff Holly was another mission specialist that did the actual releasing. Now, Jeff Holly had a story about, he'd been on every great observatory that was launched. Hubble, Compton, and now Chandra. However, he has declined to be on the last great observatory to be launched, and that was because he said he found out it was going on an unmanned vehicle. Mm-hmm. So anyway, but everything worked great, and these people, let me say it again, Eileen Collins, I can't remember, I lost my thought. Eileen was the commander. Katie Coleman was the mission specialist. Steve Holly was the mission specialist, and the last one was Michel Tognini, who was a French astronaut. They did a great job. And I guess that's it. That's my story.
Okay, very good. Gene, you or Martin got anything y'all want to?
I guess the thing I remember most is that we were scheduled to be launched on the shuttle, and then they had to scrub it. I think it was because of bad weather or for some reason they had to scrub it. And then they got us on a telecon and said, hey, if we try one more time and can't launch this thing, we're going to stand down for about 3 or 4 days to rest the crew and whatever else they do. And they said, you've got to do something to help us open up that launch window so that we can have a higher probability of launching on this next attempt. And we argued with them that we already had all the design margin that we could that was given up, and we were tight, and we cried and moaned about it. And they said, no, we want you to open up your part of the launch window so that we can increase this launch probability. So we worked all night trying to cut down on all the dispersions that we'd assumed on the performance of the propulsion system, and looking at the estimate of the mass and all kind of things. So we gave them a few more minutes, open up the launch window the next morning, our daylight in the morning conversation with them, and so they finally agreed that we'd given our ounce of blood, so they would try again to launch it. And I realized in that conversation how much pressure can be brought to bear on people when they've got the center directors from about 2 different centers there, and you got the astronaut corps and all these people breathing down your neck and make you sweat, make you wonder what you're doing here and why you got yourself into this kind of a spot. But it worked out good, and we did get it off the ground. I remember also that when we had the launch and everything was starting, we had our first light, literally real-time first light. And we were all crowded in there trying to look at this display. And I was curious. I'm an engineer, and I was just kind of curious on what it would look like. I mean, it's just interesting. But the scientists were that was their meat. And when they showed that first light picture and it was clear, those guys went completely crazy. I mean, they were really ecstatic, and they've been happy ever since. But that was a real good first light, and I saw one, and it was good.
It's good.
Well, there was something else on first light. That was the first picture that Chandra had taken, and a discovery was made. In the center of that picture, never seen before, but looked at by many, many ground observatories and other optical observatories, they found something never seen before. Martin?
Yeah, Fred's alluding to the official first light, which was a picture probably has been flashed up there of an exploded star where there's all kinds of debris heated to millions of degrees, emits X-rays. Beautiful picture. But there at the center was this little dot, and that little dot was a neutron star. Star as massive as the sun, but nuclear densities about 20 miles in diameter, that had been supposed to be there but had never been seen before. I have so many favorite stories from the launch that I don't want to take up all your time, but I think one of the most interesting ones was a factor of the crew and the launch and the attention that Eileen got, which was really wonderful. It really was. Hillary Clinton came, the women's soccer team came, Judy Collins came, wrote a sung her song, etc. Nobody was asking us, hey guys, this is very suspicious. Is Marshall Space Flight Center and putting up a telescope, and didn't Perkin-Elmer build the optics, and didn't you guys screw it up like you screwed up Hubble? Nobody asked us that question. They were all interested in Eileen, and thank goodness for that. I think a very amusing thing was when we were there at the opening ceremonies and we looked behind us, and my daughter-in-law turned around and said, "Oh my God, that's Fabio." And she kept looking back at him, and she went over and finally got up the nerve. We took a picture of her with him, and it turned out, if you've seen a picture of the crew, Katie Coleman, the mission specialist, was quite an attractive young woman. Not that Eileen wasn't, but you know what I mean. And the rest of the crew had taken her picture and sent it to Fabio and invited him to the launch on her behalf. And so he did come, and then they explained it to him, and he took it like a good guy. So that was quite an incident that I remember.
Martin, while you've got the mic, let's talk a little bit about the science. What do you see as some of the major discoveries over these past 15 years? What really sticks out to you?
Oh boy, that's a tough one. But I think the two areas that certainly stick out in my mind, because they are what is driving not only our interest as astrophysicists and astronomers, but also the public interest, and that is trying to understand two important things: dark matter and dark energy, which are very different things. Dark matter is matter. We know it's there. We call it dark because we can't see it. The only way we know it's there is from its gravitational effect. It's what holds the clusters of galaxies together. You saw that bullet cluster perhaps, and it's not interacting with itself, yet about 20% of the energy density of the universe is made up with dark matter. Only 4%, tiny little bit, is normal matter like you and me and stars and etc., tabletops and microphones. We're trying to understand what dark matter is, and it's a very important question because we don't know the answer. And then even more on the gosh gee whiz scale is trying to understand dark energy and its implications for how the universe is going to evolve, and also trying to answer the question, why is the universe the way it is? The universe is accelerating apart. This is something we only discovered, I don't mean we, but was discovered in the last 20 years or so. And Chandra, however, has been able to make major contributions to understanding the parameters, getting out the numbers to help us in this endeavor. And it's not the only thing that helps. Hubble is important. The microwave background studies are important, but all together we're getting a handle on the numbers, and hopefully getting a handle on the numbers will eventually get us a handle on the understanding. And as I said in the video above, it's extremely interesting that if you take the general relativity theory that Einstein created in early the 20th century, and put back in what he called his greatest blunder, the cosmological constant, because it has the universe accelerating apart, and he didn't like that, and he didn't know that it was. It's exactly works out that the current numbers are consistent with his theory to a T. So I think those are the two most important areas that Chandra is working on today, but if you talk to somebody who's interested in how stars form, it's talk to somebody who's interested how planets form, et cetera, they'll give you different answers.
Okay. One final question before we turn it over to the audience to invite questions from them. I think everybody will be very interested to know what's the current state of Chandra, and how long can we expect that Chandra will continue to operate and produce outstanding science?
I think that's an unanswerable question. As long as it's up there and functioning, I think it'll be doing great science. But how long can the equipment hold out in every aspect? I can't answer that. I don't think anybody can. We hope it lasts very long. And to some degree, I think we have a last laugh at Congress because they forced us into a 5-year mission, and we've been up there for 15 years, just as long as the initial mission of Hubble.
Very good. Okay, with that, we'd love to have some questions from the audience for our panelists. Yes, right here in the front.
I have a question which is more geared toward looking at your pictures and using them in education once you put it on. And that is, I'm used to looking at color and using it to determine energy. How do you decide on the color that you show? Is it energy or is it number of photons that are hitting your image?
That's a very good question, and the answer is both. Depends on the context. Obviously, there are no colors associated with X-rays, and often we show images where we're only talking about how bright things are. So we use a color scale, and that color scale is up to the scientist who's writing the paper or making the image, and you see all kinds of things. But often we also, with Chandra, with most of our instruments, we are measuring the energy of the X-rays. Then the color code is more complicated. And we do indicate the energy by the color and also the intensity by the relative brightness within that color.
Any others? Here. If you could speak loudly, please.
Lessons learned. I imagine you use some of those lessons learned with James Webb telescope. Is that?
Yeah.
Are there other missions too that's going to be used for?
Let me answer that in part, and I'm going to ask Gene to take it. For those of you who don't know, Gene referred to doing consulting work. Gene actually chairs the standing review board for the James Webb Space Telescope, so he's very involved in what's going on there and has taken a lot of the lessons that he learned from managing the Hubble program and Chandra program and helping that project team apply that to the James Webb Space Telescope. But Gene?
Yes, one of the earliest inputs that the Standing Review Board had on James Webb Telescope back in 2002, I think it was, when I first started chairing it. They are just beginning to organize the James Webb to decide what contracts would be let for how they're going to break it into elements to be developed. And one of the things we told them right up front was that you need to start right now deciding that you will have one database to operate this thing with and not allow all the different contractors, and there's half a dozen of them, to develop their own. But if you don't make that decision right up front before you start letting contracts, you're lost. You'll never be able to recapture it. So that's one lesson learned. We've also been applying to James Webb, which I'm most familiar with, the multiple cross-checks on the hardware and software, and the testing and the verification phase. So there's a lot of these lessons learned that are being applied across the agency, I'm sure. I know there's a number of programs that I've been associated with since I retired that had a single database, and they all working very well as far as the amount of effort that you put into it. NASA encourages each program to review the lessons learned from other programs. In fact, we've been criticized as an agency many times from not going in and trying to learn and reviewing and making sure that managers in new programs have access to and review and try to apply where it's appropriate the lessons learned from all these other programs. So it's a concern within the agency that these lessons learned be used properly. Every program's different. Each one has their own unique problems, but many of these lessons learned are somewhat generic. So there's quite an effort going on within the agency to try to take advantage of this.
Okay. Others? Here.
You said that you calibrated the instrument here at Marshall Center, and was it mostly designed here, and were there other centers involved?
Well, there were other centers involved in the program. For example, Goddard, which would give us the ability to communicate when Chandra was at very high orbit. But as far as the calibration, like going back to what Martin said, that was very, very important. If you're doing visual sightings and observations like the Hubble, you definitely don't have to do this kind of calibration. It would be nice if you could, but in any event, when you do X-ray observations, you're going to be looking at things that haven't been charted by Galileo, for example, and so they know everything about it, how big it is, how what its spectrometry shows on it, the materials it's composed of, et cetera, et cetera. X-ray is going to be looking at things that nobody's seen before, and they can't look at objects that have been observed for generations by different telescopes. So calibration is a must. You can't live without it. Without it, you're going to be looking at things you won't know really what you're seeing.
Let me add to what Fred said. The design of the telescope was, although various team members had definite responsibilities, was really a team effort that involved engineers at Smithsonian Astrophysical Observatory, the Marshall Space Flight Center, Eastman Kodak, the company that built the optics, Perkin-Elmer, and also our prime contractor, TRW. And there were multiple cross-checks and inputs to the design. I don't think anybody could claim that they designed it. And I would like to add to that, although he's now deceased, is our telescope scientist, who is part of the science team. Leon van Spabroek played an enormous role in the details of the telescope design, and he brought his experience from the Einstein Observatory to bear on this new telescope. But really, he brought his genius and brilliance to bear. And I should also mention, well, there's so many people to mention, I won't want to embarrass them. And then I probably leave someone out. But that was a team effort, and that's one of the things that these guys on my left really brought to the project, not only the calibration, but they made us a team, and that was so important.
Okay. We're nearing the end of the hour. In fact, we've gone past the hour, but that's okay. If you got any questions, any other questions, we'll be glad to take those. All right. If not, in conclusion, I would like to thank the Space and Rocket Center and the foundation that's helped set this up and enable this event to take place tonight. Most of all, I would like to thank all of you for being here, and for those of you who had a part in making this program as successful it has become. I want to say personally thank you for your efforts. And hopefully you see and are able to reap some of the rewards of the work that you put into this over the years during the design and development phase. And to Martin, Gene, and Fred, thank y'all very much. Very enjoyable.